And our next speaker is Gabriel Larotonda from Universidad de Buenos Aires in Argentina. And he'll be talking about Finsler geometry of a compactly group by means of a momentum polytope. Are you ready, Gabriel?
Yes, of course.
Okay, so I leave you the floor. So whenever you want, you can start.
Thanks a lot. Okay, first I would like to thank the organizers for inviting me. This is a very nice topic, and I'm happy to be participating. And let me share my slides with you so we can begin with the talk. Can you see them?
Yeah, we can see them.
Perfect. Well, as you have probably noticed from the title of the talk, this talk is more oriented to the study of the group of symplectomorphisms rather than proper symplectic geometry. But in any case, I thought maybe some of you will be finding it of some interest. This is joint work with my student Martin Miglioli. And before I really start the talk, I really begin with the slides, let me introduce you to a very simple and motivating example of what we are trying to discuss over here. So if we are in R2 with the infinity norm, which is just the maximum of the coordinates, everybody knows that this one is the unit ball of the sphere for this norm, right? And it is a very nice polyhedra. One of the first things that you learn in geometry is that to join one point to another, the best path to follow is a straight line, right? So if I want to join 0 with this point here, I don't know, call it K, then you should probably be advised to follow a straight line because it has the following property, right? You take sigma, the segment, and it has length equal to the distance between the endpoints, right? But hey, you know, there's many other paths in R2 joining 0 and K with the same property. So the idea here is that if one tries to characterize in a way all the possible paths joining 0 to K, which has this minimizing property, I will call these short paths. Short is just a fast way to say it's a minimizing rectifiable arc joining the endpoints, which length equal to the distance among the endpoints, which is in this case is the norm of K, right? Then you could be possibly asking to characterize all these paths. I say that this one is just one possibility, and this one is another possibility, and this one indeed, well, sorry, is another possibility, etc., etc. And what is the nice characterization I'm mentioning here about every other curve joining 0 to K with a minimizing length or short path? Well, if you take the cone of this face of the sphere, this is a face, and you consider this closed cone, right? The restriction for a path gamma joining 0 to K with length equal to the distance between 0 and K, which is just the norm of K plus 0, is that its speed lives inside this face of this cone. We call it the cone K, right? Or if you want it, if you prefer to state it that way, if you normalize the speed, which is always possible for rectifiable paths. You want this normalized speed to live in the phase supporting this point K, right? Well, this is just an introductory example, but it's the guiding principle behind most of the discussions that we'll be having next. Okay, so keep it in mind, because what you are trying to attempt is trying to generalize these to compact Lie groups with B invariant metrics. Okay, so we now start the talk. The main topics of the talk will be consider some intrinsic B invariant distance in a compact, connected, and semi-simple Lie group. And this distance will be, in a way, induced by picking some polytope in the Lie algebra. And in particular, to be more specific, will be obtain the distance by picking a polytope in some choice of positive Weil-Chamber of fixed Cartan subalgebra of the Lie algebra, right? In this notation here, K is the Lie algebra of K, and H is a Cartan subalgebra. And this is by picking, this is a compact simple Lie group. You obtain this by picking a maximal torus. And the closed positive Weil-Chamber is obtained by selecting a positive set of simple roots, right? So I haven't yet discussed how you really go from the polytope to the distance, but once you have to do that, which is a very mechanical and systematic, we'll say, method, you want to, the first question you want to ask is, which are the short paths for this distance? I mean, short in the sense of their length is equal to the distance among the endpoints. And the first answer, which is rather classic in some settings, a theorem or result, is that if you pick one parameter group, like this one, which is the analog of the segment in our Lie group, right? You recognize the analogy. Then these ones are short, okay? These ones are of length equal to the distance among the endpoints. And this is true for any B invariant distance. Well, but as I mentioned before, what is more interesting at this point, now we have characterized at least one path joining endpoints with optimal speed. There are many other. So we want to have a, what you say, characterization or description of all the other short paths, right? Like in the previous example, it's easier to go this way. We have all these paths here with the condition that the speed does not leave this phase. Okay, so let's go back to the slides. And our main example for this construction of or choice of polytope would be if you take a coadjoint orbit in the Lie algebra of K, which is, as everybody knows, how would you say, the most famous symplectic manifold, or the most universal in some sense, a kind of symplectic manifold. You can take the polytope called Kirwan's polytope, which is obtained by intersecting the coadjoint orbit with some close positive Weil-Chamber of the Cartan algebra. And this is just a particular example of the general case, which is obtained by considering any closed symplectic manifold and an action by a compact semi-simple Lie group K on M, which is Hamiltonian, which it will be discussed a bit later. Then you have a momentum map, and the polytope will be the intersection of the image of the momentum map with the closed Weil-Chamber of the Lie algebra. Okay, so this one here is a particular example of this one, because for the symplectic structure given by the Sorial-Kirillov symplectic form, the momentum map is essentially the identity if you identify the Lie algebra with its dual by means of the Killing form, right? Because in this case, it is non-degenerate because it's a semi-simple compact Lie group. Okay. So now let's put some, how would you say, matter or some solids ideas behind this general discussion. So we have these objects, the algebra of a compact Lie group, and the W will be denoting the Weyl group. H plus, a choice of closed positive Weyl chamber. As I said, you have the peak system of positive and simple roots. And we now define what we call the generalized Hofer norm, which is obtained by picking a compact full ad invariant set. Compact and full means that it generates linearly all the algebra. Ad invariant means that it's invariant for the adjoint or co-adjoint action of the, right? So you want K, A, K star, or K minus 1 equal to A for any K in K. So the generalized Hofer norm will be defined as follows. Just take the maximum over the set, the full compact set, and then subtract the minimum. It's in a way, it's some kind of a diameter of the set, but with an identification with the dual. Okay, for some discussions, it will be useful to consider the Hofer's polytope, which is defined as follows. If you intersect E with the Weyl chamber, then it is, we assume that it's generated by a finite set of points, and then you take this convex capsule of the difference to make it a symmetric body, and you intersect it with the Lie algebra. Right? This is what we'll be calling the Hofer's polytope. Okay, so now you take the convex closure again, but now we take the polar dual of this set, right? And it is not hard to see that this B is in fact the unit ball for this norm. So the set of elements of the Lie algebra such that X has norm less or equal than 1 is exactly the polar dual of the convex capsule of the symmetrization of E. And it's in fact an open symmetric convex body around 0. And by constant theorems, it's if you intersect it with the Cartan subalgebra, you recover the polar dual of the polytope E. So now, as kind of a motivation for the rest of the constructions, let me discuss a bit the classical metric for the group of symplectomorphisms constructed by Hofer around the 90s. So you take any function of a real parameter and a parameter M that is smooth in a closed connected symplectic manifold, and then this one, by means of the symplectic pairing, induces this vector field, which is defined by duality, right? You take the differential of the exterior differential of H at its T. This defines a one form. By duality with the non-degenerate two form, this defines a unique vector field. Now we consider the Lie group of Hamiltonian diffeomorphisms, which is in fact not a classical group, but an infinitely dimensional group modeled by a Fréchet space. As we will see shortly, it is modeled by the smooth functions in M. That this set is more or less the Lie algebra of this group. And it's defined as follows. You can take any diffeomorphism of M, will be an element of Ham, but you want to be reached with what we call an isotopy, which is described by Hamilton's equation in the symplectic manifold, right? You have this symplectic vector field. This is Hamilton's equation. You follow the path. I didn't say it, it's missing here, but the path should start at the identity diffeomorphism. And then at the end, you obtain another diffeomorphism, and the family of all these endpoints of isotopies is the set of Hamiltonian diffeomorphisms, and it in fact forms a nice Lie group. And the norm introduced by Hofer in the 90s is this one. You take the maximum over the manifold M of the function H, then subtract the minimum, and this defines a norm in the Lie algebra of this group, which is, as I mentioned before, the quotient of the smooth functions on M divided by the constants, right? Because constants here have a zero norm. And in fact, it's easy to see that two functions that differ in one constant would induce the same vector field. Okay, there's a lot of theory around the group of the diffeomorphisms, and in particular of the study of the geometry of the group Ham with this Hofer norm. It's a very interesting subject. But for us, it's a kind of a motivational example and a source of examples. Because now we want to consider a Hamiltonian action of a compact Lie group. So now we have this symplectic manifold, we have a compact group. The action will be denoted as usual as follows. And we say that the action is Hamiltonian if for fixed K, this diffeomorphism is a Hamiltonian diffeomorphism of the group. And equivalency, this is rather technical, so maybe you can now skip it. But there is a condition that there is a momentum map, which is, of course, natural, intertwining the two structures, the Hamiltonian action and the coadjoint action of K. Here you have, for each X in the Lie algebra, you consider the one parameter group in K, you push it to the diffeomorphisms of M by means of this isotopy. This gives a family of elements in this group, and then you differentiate at X at T equal to 0, and you obtain a symplectic vector field. And this is a relation you want. One most important for us will be considering almost effective actions, which means that it does not necessarily mean that the action is injective in this map, but its differential is injective. So we want this assignation from a vector field here, from the vector here in the Lie algebra of K to the vector field X sub M to be injective. And with this injective map, we can pull back Hofer's norm. Pull it back in the classical way. You define the norm of an element here in the Lie algebra, you push it forward here, and you give it Hofer's norm in the end. And not surprisingly, what you obtain at doing this pullback of the norm is you recover the Hofer norm we defined before with the set. Remember, there was a compact full set, etc. The image of the momentum map of M inside the Lie algebra of the compact group K. And now by Kirwan's theorem, this is certainly a convex polytope. So this is our main source of examples for the construction of Hofer's norms, right? Now, this is what we call the momentum polytope. And we have discussed norms in the Lie algebra. Here are norms in the Lie algebra of the group K. How you go from a norm to a distance? Well, this is a very classical procedure. You take any, in fact, ad invariant norm, not necessarily ones we are considering here. And then for any smooth path, let me use the subindex to denote the variable t, which is smaller, and I think it's nicer to read, simplify the notation. And then you compute the length of the path by differentiating and translating with the group action to the origin of the Lie algebra. So you now have an element of the Lie algebra, and you can measure it, and then you integrate in the classical sense. Maybe you should ask less than smooth, piecewise smooth, or even Lebesgue, the differentiable almost everywhere, etc., etc. And if the norm is ad invariant, you can conjugate here, and of course this number will be the same as this one. Well, now that you have defined the length of paths, it's easy to define the distance by taking the infima of the lengths of paths joining them. This is what we call an intrinsic metric, right? Because you define the distance as the optimal way of going from one point to another. And this distance is B invariant because if you conjugate or if you move around with U and W, it doesn't move the distance. So this property follows from the add invariance of the norm and the definition, which is a left invariant metric in the group. So what is a geodesic in this context? You know, in the classical setting of Riemannian manifolds, when your tangent norm comes from an inner product, which is not the case here, you see there's nothing Riemannian about the maximum of something. You usually define a short path or a geodesic as some kind of variational principle applied to this functional length. And then you have something that obeys a differential equation. Here we take the other approach introduced by Gromov and others, which is you define a path as a geodesic or short if it's optimal, if it's minimizing, if its length measured like this is equal to the distance among its endpoints, as I discussed at the beginning of the talk. That was our natural definition of short path or minimizing path among endpoints. Okay, now we have established that we have a tangent norm in the group, which is this one. We have defined our length, we have defined our distance, we have our notion of geodesics. And the first question is, well, can you say something about geodesic? Well, yes, of course. As I mentioned before, there is some kind of classical result for the unitary group and then adapted to other compact Lie groups, which is if you take this one parameter group, it has, of course, constant speed. Its length is the norm of the exponent. And modulo some restrictions of not going too far from the identity, then it's easy to prove in general, or well, I wouldn't say perhaps easy, but it's natural to prove in general that for any other path joining the identity and the endpoint of delta, you will have this length of gamma greater than the length of delta. So you see this inequality tells you that this is the best possible solution for the length of path joining 1 and k. And therefore, this segment or one parameter group is a geodesic on joining these endpoints. This result was in fact obtained first for the group of unitary matrices, then was generalized for certain Lie groups. Then there were several generalizations to infinite dimensional unitary groups in acting on Hilbert spaces. And recently we generalized it to any compact Lie groups with Martin. Now, the main topic, it's been a long way, but the main topic of this talk is, can we give a good description of all other geodesics joining 1 and k? And before I proceed, let me tell you that what follows is kind of showing that in fact, in most cases, the situation is almost exactly what happened in the first slide of the drawing with the R2 with the maximum norm, right? Remember in that case, the speed had to leave, that's the speed of these curves should not leave. You draw the speed here, you have the speed here, you draw it in the origin, it's here. It does not leave the cone or normalize it, it does not leave the face. This is very nice, which I think is a very nice result because usually the geometry of the Lie group is much more complicated than the geometry of a normed space, right? So we go back to the slide where we were before. I think it was over here. So other geodesics, what do we know? Take any path, and as you know, without loss of generality, this can be reparametrized with constant speed, which is kind of useful in our setting because we are not interested in finding the function from the real line to the group, but we are interested in the image of the function, right? Because you can, for a given path, there are many ways to reparametrize it, But in any way, any reparametrization will be giving the length, the same length, right? So we are not interested in the function, but in the image of the function. So it's natural to reparametrize with constant speed, which is the length of the speed. And then if it is a necessary condition for gamma to be a geodesic of the D group K with a Hofer norm, then not the speed, but the logarithmic derivative of the speed, which is this object here, which you see it is an element living in the Lie algebra, okay, must stay inside the face of the ball of radius L for the Hofer norm, which is exactly this picture as before. So the curve, if it is a geodesic, its logarithmic derivative must live inside some face. The speed can move around here, but it can never leave. The moment it leaves, it loses its optimality. And you can rephrase this as follows. This is an exposed face, which is obtained by intersecting the sphere with a hyperplane. It would be the preimage of the number L by a linear functional of norm 1. So equivalently, you would have a unit norm functional such that phi of the logarithmic derivative is constant and equal to L for t in the interval. Okay, so if gamma is a geodesic, its speed must be here. And the other way around, it's more or less the same with some technical observation. That is, if you take any path and the logarithmic derivative stays inside the face of the ball, but it's not too long, then it will be a short path. So the condition is the same with the addition of this condition, which is more or less obvious, right? Because, for instance, if your group is the circumference, most trivial example of all, this will be a short path, but up to a certain point, if you pass over here, it would be not a short path because the optimal way to go here is not this one, but this other one. This is what we call the radius of subjectivity of the exponential map in Riemannian geometry. Well, it's kind of this analog. You cannot go too far, but if you don't do that and your speed or your logarithmic speed stays inside the face of the ball, then the length of the speed of the curve is optimal and it's a geodesic. So now we have characterized all geodesics, but there is some obstructions to these characterizations, which is very nice, because you don't have the condition on the speed of gamma, but on the logarithmic derivative of gamma. So what's the next step? Well, you have to study how is the behavior of the faces of these Hofer norms, right? You want to understand this polytope, and you want to understand how to say this geometrical condition in more perhaps natural terms using the Lie algebra structure, or maybe the conditions on the polytope, etc. Okay, first a remark. If you have an almost effective Hamiltonian action as before and take any smooth path, you can push it forward to the group of Hamiltonian diffeomorphisms by acting on M, right? This is a path in K. If you act on M, you obtain, in fact, an isotopy, a diffeomorphism M, which is Hamiltonian diffeomorphism. So you have a kind of correspondence between path in K and path in the group of diffeomorphisms. And the theorem is that, sorry, gamma is short in K if and only if the isotopy is short in the group of Hamiltonian diffeomorphisms for the Hofer metric. Of course, this result is clearly expected because it is very easy to establish this result in the setting of Riemannian metrics. If you pull back a Riemannian metric, there will be a one-to-one correspondence between the geodesics on one side and geodesics in the other. There is nothing Riemannian in this context, right? Just think of the L infinity ball, which is a square. There's nothing remaining about it. So this is a very nice correspondence, and it shows that this is a very natural way of geometrizing the group. This corresponds with geodesics in the group of Hamiltonian diffeomorphisms. So to finish the talk, let me discuss a bit more how this polytope, this Hofer polytope, has to do with the structure of the geodesics. We know that to be a geodesic, you have to have logarithmic derivative inside the face of the sphere of the Hofer norm. So remember that you can recover the unit ball of the Hofer norm by taking first the convex capsule of the momentum map, of the image of the momentum map, then you symmetrize it to make it symmetric around 0, and then you take the polar dual. And the other definition that was important, which is what we call the Hofer's polytope, which is, well, you take the convex capsule of A here is mu of m again, and you intersect it with the fixed Cartan subalgebra. Well, the theorem here says that all the faces of this polytope, or of the unit ball, are abelian if and only if all the extreme points of P are regular. Sorry, regular means that in these settings, for instance, that the adjoint representations has all different eigenvalues, no repeated eigenvalues. This is the Lie group notion of regular, or Lie algebra notion of regular elements. So if you have a good knowledge of the Hofer's polytope, which is obtained by intersecting the image of the momentum map with the Cartan subalgebra, then you can obtain good information on the faces of the ball. And so if you start with the Hofer polytope, which is all its extreme points are regular, then you can conclude that the path gamma in K is a geodesic if and only if the exponential of some path in the Lie algebra with the property that the path lives in the commutative subalgebra, and moreover, the length of gamma is also optimal in the normal space. So you see, when all extreme points of the polytope are regular, there is a one-on-one correspondence between geodesics of the normal space and geodesics in the Lie group. So in this case, it is exactly as the Lie group is behaving exactly as a normal space, which I find very amazing at the beginning, and then very natural now that we have discussed it a lot with my colleagues. So you know, then in this case, you have the curve living here. Usually this logarithmic derivative is not equal to this, because the differential of the exponential map is usually very complicated in Lie groups, right? But if the gamma lives in a Lie commutative subalgebra, then this is easy to see. And moreover, since this path has optimal length, it has the same length that the curve below. So in this case, the exponential map acts as an isometry between the tangent space, the Lie algebra of the group, and the group. And as I mentioned at the beginning of the talk, the geodesics in a normal space are characterized. I mean, this example here is generic in the following sense. If you want to join 2 points in the sphere, 2 points in the space, you take the sphere around one of them, then you can use any path that its piece that does not leave the, where is it? Sorry, does not leave the face. It's easier to go from here. So I'm almost finished, don't worry. The clock is ticking. Yeah. This is what I mentioned before. This is a very nice folk result. You can prove that geodesic in a normal space, the path of optimal speed, it's optimal if and only if its speed sits or lives inside the face of the sphere. I'm assuming the geodesic is parameterized by a constant speed. If that is not the case, you have to replace word phase here by the cone generated by the phase, right? And to end this talk, in the particular case where the symplectic action is the classical coadjoint action of K in its Lie algebra, you take the coadjoint orbit of lambda. Here it should read -1. I was thinking about the unitary group, but this is valid for any compact semisimple Lie group. You take the coadjoint orbit of lambda. You consider the natural action of K here. This is a Hamiltonian action. This is a symplectic manifold. And you ask that the orbit is regular. There are other results for non-regular orbits, but you need to, for this precise statement, for lambda to be regular. And then the path gamma will be short for the Hofer metric of this particular action of a regular coadjoint orbit, if and only if the logarithmic speed of the path is contained in a Weil chamber of the Lie algebra, which is, as I mentioned at the beginning of the talk, given by a choice of a torus first, which gives you the Cartan subalgebra H, and then you have to pick a positive, a set of positive simple roots there. So you see here the description is in terms of the Lie algebra structure for any coadjoint orbit which is generated by a regular element. Okay, that's all I have to say about that. And I want to thank you very much for your kind attention.
Okay, thank you, Gabriel, for that talk. It was really nice. Does anyone, well, there's people clapping their hands virtually. There's something I should have mentioned in previous talks as well. So are there any questions?
I have a question. Hi, Gabriel.
Okay, go on.
I was wondering about the conditions. I don't know. I think you maybe stated them, but so the conditions on the Hamiltonian for the gamma, for the speed, for it to be short.
You mean
here? Did you specify, was there specific conditions on the Hamiltonian at all, or was just?
I'm sorry, but I don't fully understand your question. You mean which kind of action, or sorry?
Yeah, I guess so.
Let me get back to the beginning. This construction, which is a particular case of the general construction, you have to ask specifically for the following. Here is the slides. Okay, you want your compact group to be acting on a compact closed, I mean, without border, symplectic manifold, right? And you want the action to be Hamiltonian. Hamiltonian means that for each fixed K, this diffeomorphism is Hamiltonian diffeomorphism.
Sure, but there aren't any extra conditions on the Hamiltonian for all of this to work in effect.
Yes, the extra condition, recall that there's a kind of a strong restriction here because we are starting with a compact semi-simple connected Lie group. So that's one big restriction, okay? And the other one is you want the action to be almost effective. That means the action have a discrete kernel or equivalency that the differential of the action, this assignation here, is injected. This is to be able to pull back the metric to the group.
Okay.
But that's all. That's all that we need.
Oh, I think I was alluding to its autonomy. Hamiltonian's autonomy. No,
this is for all Hamiltonians, because you see in this discussion we are discussing the group of Hamiltonian diffeomorphisms, and this is constructed by using usually non-autonomous Hamiltonians, right? Because for the construction, you start with this is maybe we should have gone slower for this part. How to construct the group of Hamiltonian diffeomorphisms, right? Yeah. So you start with any Hamiltonian, autonomous or not. Maybe it's constant on this variable or not, right?
Okay.
But you start with any of these. And then this induces a vector field with the duality given by the symplectic form and this one, right? So for any Hamiltonian, autonomous or not, you have a vector field.
Mm-hmm.
And now, with these vector fields, you're able to pose Hamilton's equation, right? And again, the Hamiltonian could be autonomous or not.
Okay. So basically, there are no conditions. It's basically almost any Hamiltonian.
But there is something very interesting.
Okay.
What do you get if you start with a Hamiltonian diffeomorphism? You remember maybe you don't, because I speak very fast and very badly, because
no.
It's been a while since I talk with anybody due to the quarantine. I'm just kidding. And I know there's another talk next. I don't want to be too.
Actually, no, this is the last talk.
Actually, this is the last talk of the day,
okay.
so
but
you
anyway,
can extend as one.
Don't worry, I will be finishing shortly, even if it's the last talk.
Okay,
so,
no problem.
You remember there's a correspondence between being short in the group K with the pullback norm and being short in the group of Hamiltonian diffeomorphisms with Hofer's classical metric.
Yeah.
Right? Okay. But this isotopy was constructed with Hamilton's equations, right? The isotopy obeys Hamilton's equations. And the Hamiltonian is autonomous if and only if this path is a segment.
Okay.
Okay, so you recover straight lines with autonomous Hamiltonians. And all the other non-autonomous Hamiltonians gives all the other rather strange family of short paths which are not straight.
Okay, yeah, all right.
Okay, thank you.
Thank you very much.
You're welcome.